now that His Highness Levi is here, we can begin. Oh, yes. He condescends from on high to join us.
I did tell you I was going to be.
Yeah, you did, but just quit your other thing early.
I can't.
I think you can. All right. So, like I said, I didn't tell you yet. I sent the wrong book. So if you try reading the book and it didn't make sense, I sent you the calculus textbook, not the logic textbook. They're very similarly named, so sorry about that. So I replied to the same email with the correct book attached. It should be called Introduction to Logic. If your book doesn't say Introduction to Logic, it's the wrong book. Let me know. So last time we just did a really quick blast through of logic that you typically do at the beginning of a geometry course, or like we did in Discrete Math. Now we're going to go back to the beginning, and we're going to go through it, and we're going to go through it a lot more thoroughly and slower. Now, one point I should probably make before we continue with this. I guess only 2 of you have taken Discrete Math from me, right? 3 of you have taken Discrete Math from me. You remember how much logic we covered in Discrete Math? How much?
A lot.
A lot. Do you feel like you're an expert on logic after taking that class?
An expert?
Yeah.
I wouldn't say an expert.
Neither would I. So, this is my warning to you. The only formal education I've had in logic was that exact course. I've used logic a lot in courses. I have a math degree and a CS degree where I use logic a lot, but I've never been formally educated on the material. And it's real easy when you're going through material for the first time to think you understand it, and when there's not someone there to fine-tune your thinking and tweak it a little bit and say, you almost got it, but you're just missing this thing. It's really hard to just understand it the first time. And the odds that what I think the book is saying and what it's actually saying always line up are almost 0. So I'm going to read something, literally what happens before we meet. I'm going to read the material, try to understand it, and then explain to you what I just read. That's what's happening. I'm not calling back to days when I was trained how to do this. I'm just reading the material, trying to understand it, and then explaining it. That's it. I'm going to make mistakes. That's a given. So you guys need to be thinking more than you would in a class where the teacher's an expert on the material, and they're teaching what they know. You need to be more critical of me. I think is the right word. So if something doesn't make sense, make sure I re-explain it until it makes sense. Because maybe I just don't understand it right. That's a very real possibility. Okay? So there's my fair warning to all of you. I might just get up here and lie to you. All right? Okay. So let's jump into the material. The author starts with a brief discussion about how we're starting our foundations of logic. So it's kind of strange, if you look at it from a high level, to think about what we're doing. We're going to use language, which we know is inherently vague, and we're going to try and come up with very precise, well-defined language. And it seems kind of weird that we're able to do that. You can use really vague language to have well-defined, precise things. Yes, you can. And the example the author gives in this is when we explain the rules to a game. For those of you that know how to play chess, you perfectly understand the rules of chess. If I go make a move in chess, you understand if it was a valid move or if it was an invalid move. We're doing a very similar thing when we're developing our rules of logic. We're going to be starting out with premises, and we're going to be applying rules of logic to those premises to derive conclusions. And we either did it correctly or we didn't do it correctly. And so we're trying to use vague language to capture what exactly it is that we can and can't do precisely. Make sense?
Yeah.
So that's where the author begins his discussion. And then next comes Sentential Connectives. So we know that we're using languages. We're going to be using sentences. The way that the author is using sentences in this book is equivalent to the way that we've used statements in the other book, or if you've done other logic courses, we typically say statements. So I might accidentally interchange those two. That's what the author means by a sentence in this book. Something that can be true or false, but not both, but at least one. And so that's what he means by sentence, and one of the first things he talks about in it is sentential connectives. And we've already gone over a few of these sentential connectives. Not, and, or, the if-then connective, the if and only if. These are some that we're really interested in, and we'll develop logic with these, but there's tons of sentential connectives out there. But is one, and then is one, because is one. Make intuitive sense what a sentential connective is?
Yeah.
It's,
Well, it sounds like a conjunction.
it's something that it doesn't always have to be just a conjunction. A conjunction is an example of one, but it doesn't have to be a conjunction in the English sense of the word, because not can also be a sentential connective.
Right.
So Mr. Jones thinks, so I have some statement, 2 plus 2 is 5. The sentential connective I could apply to that is Mr. Jones thinks, and I could pre-pen that onto that statement, and that would also be a sentential connective. Mr. Jones thinks 2 plus 2 is 5. Make sense? So, sentential connectives, these are the ones that we're going to be mostly interested in. So let's jump into a couple of them that we're already familiar with, make sure that we didn't regress in our understanding of them. Negation and conjunction. Let me make sure I follow with the book so I don't miss any conversation. Negation and conjunction are the first two that he decides to talk about. Okay, so negation. Negation. The negation of a true sentence is false, and the negation of a false sentence is true. Make sense? And it's good to always have in the back of your mind, I don't know when the author is going to have the conversation. He doesn't right here, but I assume he's going to at some point. Have the conversation of, when we're talking about the negation of a sentence, we're talking about a contradicting statement. Right? Not just a contrary statement, a contradicting statement. And the one that helped get your intuition for that I said, all swans are white, at least one swan is black. Those are contradicting, right?
Yeah.
No! No. Those are contrary. What if all the swans in the world are orange?
That's right.
When we have contradicting statements, one has to be true and one has to be false. If statement A is false, not A has to be true. If statement A is true, not A has to be false. Is that coming back to you a little bit? So when we're talking about the negation of a statement, we're talking about its contradiction. It's a very specific statement. All right? So don't lose track of that. And we remember our truth table, hopefully, for not, for negation or not. The way I'm always going to read the symbol is not. I don't know if that bothers any of you, but that's the way I'm going to read it. So we have a statement P. Statement P can be either true or false. If statement P is true, not P is.
True.
And if statement P is false, not P is. Right. The author decides to use a negative sign. And you can see it right there in the book. He's negating the sentence, sugar causes tooth decay. And he puts a negative sign out in front. And that means not sugar causes tooth decay. The author points out that when you're reading the negation sign, pre-pen it onto a statement. So if we have it symbolized, so we can call this not P. But it sounds awkward when I say not sugar causes tooth decay.
Right.
So he says you can always read that, if you just want a universal way to read it, you can always read that as it is not the case that. So it is not the case that sugar causes tooth decay. So anytime you see that negative sign or the not sign at the front of the statement, you can always read it this way to make it make sense linguistically. I will always, or I should say always, typically I will read that as not sugar causes tooth decay just because, I don't know, that's just how I read it. So I'm not going to do that, but you can think about that way, and there's your universal way of translating that if you want. Okay, so that was our brief intro and reminder of negation. Moving on to conjunction. The conjunction of two sentences is true, and I skip straight to if and only if, even though we haven't defined it yet, because it's a shorthand I'm always going to use, so get used to it. So when I do IFF, that means if and only if. Good? So the conjunction of two sentences is true if and only if both sentences are true. Otherwise it's false.
Right.
So if we have sentence P and sentence Q, P and Q is true if they're both true, right? But what if Q is false?
False.
False,
False.
false, and since they're both the same,
False.
false.
Well, it's true, they're both false.
Yep, I'll trick you. Okay, so remember, the conjunction of two sentences is true if and only if both sentences are true. Otherwise it's false. Good? The author uses an ampersand for conjunction, which you're used to in language. I'm always going to use that thing, that symbol, that upside down B, because I don't know why, it's what I'm used to now. So that's conjunction. And then before we continue on with the rest of these, let's start talking about some, we know there's other sentential connectives out there, and there's two reasons that we might not be interested in the sentential connective in this class. One is these are enough, and we don't need to add more. Another one is a lot of sentential connectives, we don't know how to give them truth values. So we get introduced to this idea of a truth functional connective. Hopefully that's the next section. Thank you. We talked about that. Oh, you must just have it as a discussion here. Okay. So a truth functional connective is a sentential connective that makes so that the resulting sentence's truth value can be determined from the component sentence's truth value. So let's try and wrap our head around that for a second. What we're saying is, and is a truth functional connective because I can determine whether the sentence P and Q is true simply from knowing the truth value of P and the truth value of Q.
So because will not be a truth function.
Great, perfect example. Let's say Leah is in the living room. Leah got here in a car. Both those statements are true. Is Leah in the living room because she got here in a car? Do you know whether or not that statement's true just because you know that the two component statements are true?
No.
No. So that's a great example of a connective that is not a truth functional connective. So that's one of the reasons we throw out a sentential connective is we don't know how to add a truth value to it. The other reason, slightly more subtle reason that we might throw one out, is when the connective seems to be operating the same as a different connective, and yet we want to give it a different meaning. So let's have a conversation with an example, and then I'll come back to that again. So let's look at never versus not and versus but. So these are never versus not, those are very similar in how we use them in English, and versus but are very similar in how we use them in our English. So let's look at one more thing. I will not surrender. I will never surrender. So we agree that those two statements mean something different, right?
No.
Yeah.
You don't?
Yes, okay.
Yeah. So there is some difference in the meaning of those statements. But what does this statement mean? Does this statement mean that I will surrender is false?
What do you mean?
Oh, that one, yeah. Never.
Yes.
Never, yes.
So if I surrender, is the statement I will never surrender true?
No.
I will never surrender is.
So let's assume I will surrender. And look at these two statements. So let's say that this is true. Or let's simplify this. I surrender. Let's say I actually perform the action. I surrender. Okay, is this statement true?
No.
No, it's false. Is this statement true?
No.
No, it's false. Let's say I don't surrender. Is this statement true?
Yeah. Maybe.
No.
I will not surrender.
I don't surrender.
That's true.
It's true.
Because you didn't.
I have no idea what.
Yeah, it's true.
Okay, maybe I made it too small. We'll use the statement, I will surrender, and not that. So we'll use I will surrender. Let's restart from here. I will surrender. So let's assume this statement's true. Okay? You with me?
Yeah.
Is this statement true?
No, it's
No.
false.
It's false. Is this statement true?
False.
No, it's false. Now let's say this statement's false. I will surrender is false.
Okay.
Is this statement true?
Yes.
Yes.
Is this statement true?
Yes. No.
No.
You see how it's weird? You kind of yes, kind of no.
No, it
You have a
is.
hard time. So the problem is, and we're touching on the problem here, the fact that you guys are split shows that we're touching on the exact problem. Either you want never to operate the exact same way as not,
Or everything.
even though we know that these two statements aren't really saying identical things, or it has to operate a different way. But there isn't really another way that makes sense other than it operating like not. So we have these other words in the English language that give just a little bit more meaning or a little different meaning, and yet we can't figure out another way to assign truth and false values than the ones we already have, like not. So you see the problem with never being a truth functional connective?
Yeah.
Never is a truth functional connective.
Right, it's not a truth functional connective.
That's because
If it were a truth functional connective, we'd have to basically treat the exact same way we treat not,
the word.
even though we agree that these are different statements.
The future.
So, doesn't quite work.
Saying never. Ever.
And similar thing with and but. So imagine a girl says, I love you, and I still love your brother, versus, I love you, but I still love your brother.
Different.
Same thing.
No.
Both of them. You've heard it too much? So both of these are kind of saying, I love you is true and I still love your brother is true.
Right.
They're both saying that both these component statements are true, and yet this one seems to be implying some subtly different meaning than this one. So if we
I feel like
get,
this is an English class, so like we're studying language works.
well, the point is, well,
Logic.
Well, it seems like that's what we do in all course.
one of the descriptions for the logic we're studying here is sentential logic. And it is very much about the language we use.
I like that.
And very much the beginning of logic is identifying which language is precise and somewhat vague, which language is somewhat vague.
So which
And
one's vague?
we're like carving out just the precise language
Never.
and building up what we can with it. Never is vague, we know exactly what not means.
What about and?
And we know exactly what it means. It's a truth functional connective.
Okay.
If I know that I love you is true, and I know that I still love your brother is true, I know exactly what anding those two means. It means both those are true, that's all it
Yeah.
means.
To me, and in that scenario, it just feels more vague than but.
Well,
Just
just
more
but.
vague.
But gives it more meaning.
Yeah.
Well, but
Because it's
What?
different.
leads up to implication.
Yeah.
The point is,
It could be she's in love with the brother. It's a woman.
I think the point is that.
The first one is not that.
The point is, if we try to make but be truth functional, the only way we could make it make sense is to treat it the exact same way we treat and.
Right.
Yeah.
So if I were to make some other symbol for but and construct the truth table for but, it would look just like this. We wouldn't really have another way to do it, but the same problem we run into is this statement doesn't mean what this statement means.
Not about the same problem and the same problem.
So that's the point. Language is inherently vague. There's subtlety to how you use it. We're trying to carve out a very precise piece of it and just use that piece and build up from there. Make sense?
Yes.
So we're not just interested in sentential connectives, we're interested in the truth functional connectives. And then again, we're not interested in every truth functional connective. We'll get to an example with that in disjunction. Did I skip over? No, we talked about that. Okay, so now to disjunction. And again, disjunction is one that we talked about last time. This is basically what it means to or together two sentences. And we already talked about how in everyday English we use or two different ways. And we call it the inclusive or and the exclusive or. So if you're saying something like, Donnie's in the living room or Donnie's in the kitchen, you do not mean that it's possible for me to be in the living room and the kitchen. You mean I'm either in the living room and not in the kitchen, or I'm in the kitchen and I'm not in the living room. It's one of those two cases. When we use or for, if a university says to get into our university you have to take physics or calculus, they do not mean that
You can't take
in the
both.
exclusive sense. Yeah, they don't mean that you can't take both. They just mean you have to take at least one of them. So that's the inclusive one. And for the purposes of logic, the or that we're interested in is that inclusive or. Now notice that exclusive or is also a truth functional connective. We know exactly what it means. It means one and exactly one.
It won't look like the other. It won't look like any other.
And so in, for example, programming, we use XOR as a logical operator all the time. We use OR the exact same way that we're going to use OR in this class, and then we call XOR for exclusive OR all the time. It's a perfectly valid truth functional connective. We're not interested in this class simply because we don't need it. We don't want to build this up with tons of connectives. But it is a valid one, and we're just not going to use it in this class. Make sense? So this isn't all the truth functional sentential connectives that there are. They're just the ones that we're most interested in. Make sense? Okay. So or. So the or that we mean in this class is the exclusive or. We mean at least one of them are true. Did I say exclusive?
Yeah.
I meant inclusive. It includes more cases as true. Okay. And then a side note that the author put in there that I don't remember ever coming across before, so I thought it was interesting. So we use a V for or. He says V because of the Latin word vel, which is Latin for or.
Interesting.
There's Ariel.
I thought it was interesting. I wonder where the V came from because I'm pretty sure that the only reason and is that is because or is that.
Right. Just flipped upside down.
Anyways, so let's do the truth table. If P is true and Q is true, then P or Q is true. If P is true, Q is false, P or Q is
True.
If P is false, Q is true.
True. False.
And if they're both false, that's strike two.
thinking up.
One more and you're out. Okay. And then, probably the most interesting or unintuitive of the sentential connectives that we're interested in is the one that we find in conditional sentences. It's the if-then. So, let's go over it. A conditional sentence is false. I don't like the way this author worded it. I should have went and got one from a different book, but you're stuck with, I'm going to follow the author because I assume you guys are reading the book. Okay, so a conditional sentence is false if the antecedent, so the antecedent is, if we're looking at P implies Q, P is the antecedent, and Q is the consequent.
Okay.
And the other verbiage that the author uses a lot is hypothesis and conclusion. Antecedent, consequent. Antecedent, consequent is probably the most commonly used terminology out there.
It was in the first textbook you sent us.
It was?
Mhm.
Yeah, see? So it's very common. Maybe it's just common in older text. I don't know. This is how I typically hear it. The antecedent and consequent. So, let's read this again. A conditional sentence is false if the antecedent is true, P is true, and the consequent is false, Q is false. Otherwise, it is true. So the author's explaining the one case where it's false, every other case it's true.
Right.
Just, he's doing the inverse of what he did over here. Here he said the conjunction of two statements is true when they're both true, otherwise it's false. No, he changed the verbiage a little bit. I don't know that. Anyways, where's my black box? So, there's the definition. Let's fill out the truth table, and that should cement in the definition. So, if P is true and Q is true, then P implies Q is, one more point of working with me. I'll always read that arrow as implies.
Right.
So there's a lot of ways that we could do this P implies Q. There's a lot of ways we could read that statement. We could say if P then Q. We could say Q if P. We could say P only if Q. We could say P implies Q. I'm always going to read it as implies. And then we'll go over a bunch of different ways of saying it and work through some examples. But, so, back to the beginning. So, true implies true is
True.
true. True implies false is
False.
false. False implies true is
True.
and false implies false is
True.
true. Okay. Usually we don't get it like that. No mistakes on this one.
I didn't talk.
Okay. So let's try to rewrap our heads around why each of these is the case. A true statement implies a true statement. That one should be pretty intuitive. If Donnie's holding a red marker, then Donnie's holding a black marker. That one's pretty intuitive. This next one's also pretty intuitive. If Donnie's holding a red marker, then Donnie's holding a black marker. That's false, right? And then these two cases are the one where it's awkward. Huh? Let's make sure it makes sense. So.
Okay.
Yeah,
never
it was
mind.
false, yeah.
I was looking
I
at
always
your
get
hands instead of
confused.
listening to your words.
If Donnie's holding a red marker, then Donnie's holding a black marker.
It's not being red, so it's true.
Is it true in this case?
That is true.
Why is it true?
Because you're holding the black.
That is true.
Obviously true is one way to think about it. I'm not holding a red marker.
So you can't.
It says, if I'm holding a red marker, then I'm holding a black.
It's not.
Well, I'm not holding a red. So is it false?
No.
No, then it's true. If it's not false, it's true. That's what not false means, right? And then, if I'm not holding any, it's false.
It's true.
It's true. Good. And one more way I like to cement that point is, if I start a statement with, if Donnie is a purple dragon, then, it doesn't matter what we finish that sentence with. You can say, then anything you want, and that will always be true. Because Donnie's not a purple dragon. There's no cases to check. It's vacuously true. Good? Okay, so now let's get comfortable with the English we use to capture this implication. So P implies Q can be stated in a bunch of different ways. If P, then Q. I think you guys are most comfortable with that one, right?
Right.
Here's one that you're probably struggle the most with. P only if Q. Well, it's when we think about these two. If I say Q if P, what's that saying? That's saying if P's true, then Q's true. The weird one is P only if Q. That's saying if P's true, then Q's true. And I came across a great sentence to help cement that point home. Let me see. What was it? It was something like, there's, I'm just looking at the board to remember my memory how it was worded.
Well, what was the sentence vaguely?
Yeah, it was with fire and oxygen, so let's think.
Oh,
I'm going to do the if version first, because that one will make the most sense. So Q if P. So there's oxygen if there's fire.
Oh, yeah.
And then there's oxygen only if there's fire.
Right,
That does make sense.
So, if and only if do not mean the same thing at all. They mean the inverse of each other.
Hey, and only if there's fire, there's other.
Yeah. So there's oxygen if there's fire means that if there's fire, then there's oxygen. There's oxygen only if there's fire means if there's oxygen, then there's fire. Your brain intuitively knows that this is wrong and knows that this is right, so they're not saying the same thing.
Yeah.
So this one's saying if we call over here A and we call over here B, this top one's saying A implies B,
Right.
where there's fire, there's oxygen. This bottom one's saying B implies A. I should have labeled those different.
Well, no, that bottom one's saying A implies B.
No, it's not.
Or sorry, B implies A, yes.
It's
Sorry.
saying
You should have it.
there being oxygen implies there's fire. Yeah, I should have changed my labeling. I should have called the first statement A like a normal person. There's oxygen is A, there's fire is B. This is saying B implies A. Where there's fire, there's oxygen. This is saying A implies B.
Which,
This is saying where there's oxygen, there's fire. We intuitively know that this is false and this is true. But more important than understanding that this is true and this is false is understanding that this is saying there being oxygen implies there's fire, and this is saying there being fire implies there's oxygen. So you did with how only if means A implies B, and if means B implies A.
yeah.
Making that connection?
Mm-hmm.
Because this is the verbiage that's never going away, because obviously we're going to get to if and only if. Good with that? Haven't been following along in the book. Disjunction or P or Q. Implication, conditional sentence. Oh, and good thing I scrolled to that because the author reminded me of another point. So one of the reasons this only if is so confusing is because in everyday language we sometimes use it wrong. We use it the same way we use if. And rather than me writing it out, we'll just look at the statement right here. If Mary loves John, no, that's not the one he uses. It was something like, Jack dates Jill only if Jane is mad at him. So this is the wrong way of using the only if.
Seems right to me.
Jack dates Jill only if Jane is mad at him. That does not mean if Jack dates Jill, then Jane is mad at him.
No.
That means if Jane is mad at him, then Jack dates Jill.
Yeah.
That means the same thing as this.
Right.
So we use this only if two different ways in the English language. We would say that that was the wrong use of it, the only if there. That was incorrect usage of only if, even though we sometimes speak that way. So that's one of the reasons that it's so hard for people to first wrap their heads around what the only if means. So I'm glad I found that fire oxygen, because that just makes it very clear to the brain. Okay. So let's make sure we went through all these. P implies Q is the same thing as if P then Q. It's the same thing as P only if Q. It's the same thing as Q if P. We went through over all those. P implies Q is the same thing as Q is true, provided that P is true. That's saying if P is true, then Q is true. Q is true, provided that P is true. Does that one make sense?
Yeah.
Makes sense, yes.
Okay. And then P is a sufficient condition for Q, which means what was the example I gave for condition and necessary? Oh, just fire and oxygen getting out to it. So there being fire is a sufficient condition for there being oxygen. If there's fire, you for sure know that there's oxygen.
Yeah.
But there being oxygen is only a necessary condition for there being fire. You have to have oxygen to have fire. It's not the only thing you have to have, but it's one of the necessary conditions.
It's starting to stack up.
So that you understand how Q is a necessary condition for P is the same thing as P is a sufficient condition for Q.
Yes.
Do we need to read it again?
This statement puts fire in my brain.
There must be oxygen there.
Clears it up.
There being fire is a sufficient condition for there being oxygen. Means the exact same thing as there being oxygen is a necessary condition for there being fire. If you have to have oxygen to have fire, then if you have fire, you for sure have oxygen. Make sense?
Yes.
That's what we mean by necessary and sufficient condition. And that's another way that people say if and only if a lot. They say A, if and only if B. Another way that they'll say that a lot is A is a necessary and sufficient condition for B.
Okay.
Make sense? Okay.
Well, it seems like, I could be wrong, but it seems like necessary. I'm confused what sufficient means. Meaning,
That's all you need to know.
all I need to
All you need to know is that P is true to know that Q is true. P being true is enough information to conclude that Q is true.
Okay.
That's a better way to say that. Which is what the truth table here says. Anytime P is true, Q is for sure true. If the implication is true.
And then actually be saying
So saying that
Q.
P is a sufficient condition for Q is saying that P implies Q. So if I know P implies Q, that means anytime P is true, Q is true.
That's not true though.
It's not.
Look at number 2 on your logic table.
The P does not imply Q here. P implies Q is false in this case.
Right.
So if P implies Q, now we're looking at one of 3 cases,
Right.
these 3,
And P is true.
then P being true is enough information to conclude that Q is true.
And there's only one case. Okay, yes.
And then Q is a necessary condition for P, is saying the exact same thing. P being true is enough to conclude that Q is true.
Well, isn't it saying that Q being true? It's similar saying Q being true is something important to know that P is Q.
It's
P is Q,
required.
but it's not. It's required, but it's not all you need to know. Kind of. Right?
If Q was a necessary condition for P, then if P's true, Q must have been true.
Right. But if Q is true, then it doesn't give you enough information.
Yeah, it's not saying Q, you're not concluding anything from Q being true.
Right.
In either of these cases, you're concluding something from P being true, because they're saying the exact same thing.
Right.
They're both saying knowing P is true is enough to know that Q is true.
Right.
Because
Your
they're
fire-
both different ways of saying P implies Q.
Fire and oxygen works just fine.
Yeah, I like that example.
Oxygen is a necessary condition for fire.
Yes.
Oxygen is a sufficient condition for oxygen.
Yes. That clicking?
Yeah.
Wonderful. Okay, so that was as much as I could fit on here. I should have used this space right here. Didn't realize that until after I'd written this. So now, you get to watch me erase and just write as we go. Tough life. Fun. Name of the chapter, by the way, is just Sentential Connectives. That's why. That's in a box.
I've literally been grazing all day.
You what?
I've been grazing with the Benson, with a torch, right? And it blows my mind what? You have oxygen and then you have a flammable gas, right?
Okay.
It blows my mind what oxygen will do to a flame. Like you'll turn up the gas, right? And it will just turn up oxygen. Like, because not all of it is combusting. Not all the gases, or as fast.
That's interesting. I didn't realize that you weren't burning all the gas that came out.
You weren't, right?
I didn't realize
That would be my only case. Tell me if I'm wrong. You're shooting, so you have one valve, shooting gas, one valve, shooting oxygen. Shoot your gas and it's going, and then shoot your oxygen and it just explodes.
I don't know if it somehow like decreases the inward pressure either, so
It
like
gets-
more flows out,
Benson says it gets hotter the more oxygen you put on it.
or it just burns quicker, so it gets hotter instead of spreading out burning. I don't know. Have to think about that.
There's more to burn, right? The oxygen,
Anyways.
you're burning the oxygen.
No.
Well, the oxygen is just reacting with the carbon chain. And once you use up the carbon chain, you use up the carbon chain. It doesn't matter how much oxygen you have. So. But that's
I mean, you're blowing
chemistry,
fire and it's
not logic.
Yes, but that makes more sense.
Anyways, continuing.
Right?
Like,
What I'm saying is, with a controlled flame, it's
And
still significantly.
I'm going to skip over some of his conversation that he gives with
She's marked.
if-then statements. He gives some more conversation in the book, talking about why we allow for these cases to be true. So these were the cases that on an implication that feel awkward to us, right?
Yeah,
If Donnie's a purple dragon, then the house is on fire.
true.
We're going to call that true, even though both the statements are false. So there's some awkwardness to that, and he doesn't ever introduce a conversation of accuracy through here, which is kind of interesting. The way he goes about justifying this is basically with, in a wordy way, saying it'd be awkward if we didn't allow it to be true. Furthermore, in math, we're typically only care about these two cases. We're going from true premise and showing that those imply something true, or we go from true premise and show those imply something false when we're doing like a proof by contradiction.
Right.
And therefore our premise has to be false. Or our implication has to be false. Anyways, so he kind of says, it'd be weird if we didn't. Furthermore, we rarely care about these two cases in logic and in math. And science for that matter. So that's his justification, which I felt was a little weak. I like the vacuously true better. But you can read his conversation there. And then he goes over some basic ways of encoding it. He explains the difference between what we mean by if and only if. We talked about that. And we talked about sufficient and necessary. Now we get to equivalence, or a biconditional statement.
Sentence.
Huh?
Sentence.
Biconditional sentence, yeah. So, a biconditional, let's find his exact definition. He usually puts it in fancy text for us so we can read it. So just read that for me real quick so I can write it.
Is it true?
A biconditional is true.
If and only if.
I like how he's using it in the definition.
Its two members are either both true
Should read that.
or false, I guess. Excuse me.
Yeah.
It doesn't. It's cut off.
It's. That was really.
Are
Either both true or is all we can see.
And I don't see what else it would be.
yeah. That's exactly what it is. Okay.
True or true.
So, biconditional, it's true when both have the exact same value, so maybe we'll write it out real quick and then we'll have more conversation about it. Well, no, I want to say this. A biconditional is a conjunction of two conditionals. And I don't know if he introduced converse yet. Probably did. Should have talked about that before we say biconditional. So if I have the statement A implies B, the converse of that is B implies A.
Right, we went over that last week.
Right? So when you flip the implication around, that's called the converse. And just because A implies B is true does not mean B implies A is true. As we saw with the fire and oxygen example. The converse of fire implies oxygen is oxygen implies fire. One's true, one's false.
So if they're both true, it's an if and only if. There.
So, when we talk about a biconditional, we're talking about the conjunction of an implication and its converse. And the symbol that we're going to use for it is a back and forth arrow. So maybe we'll write out the truth table here and just show everything that we're saying and we'll go. So here's A, here's B. We're going to look at A implies B. We're going to look at B implies A. We're going to look at A implies B and B implies A. And then finally we're going to look at a biconditional using his definition here. Our symbol for a biconditional is a back and forth arrow like that. Okay? So, we can have false, false, true, 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 false, false, true. Potentially give it to you in a weird order.
Yeah.
So you have to think about the implications. Alright. So really quick, let's fill out over here using the definition, not using the fact that it's a biconditional. So
false, true, false, true.
False, true, false, true. Right? It says that a biconditional is true when both its members are both false or when they're both true. So here's when the biconditional is true, here's when the biconditional is false. Make sense? Just going off of the definition. Now let's actually derive it as a biconditional, a conjunction of two conditional statements that are the converse of each other. So false implies true is?
True.
False implies true?
Yes.
Okay. False implies false?
True.
True implies false?
False.
True implies true?
True.
Wonderful. Okay.
False.
True implies false is?
False. True. True. True.
You didn't even think about those three.
You're right.
You don't have to.
Alright. And now we're going to take the conjunction of these two statements. So we're taking the conjunction of these two right here.
Right.
So true and false is?
False. True.
True and true is?
False.
False and true is?
True.
True. And notice,
They're logically equivalent.
they're logically equivalent. They give the exact same values no matter what the statements A and B are. Good?
Yeah.
Alright, so that's why we call it a biconditional or equivalence. No, we're still there. Okay. I forgot. Did I say I was going to do something after that? And go back to it after we did the truth table? What was I saying right before I started the truth table?
Converse. The old converse.
I said the converse. Was that all I was going to do? Maybe that's all I was going to do. Okay. And then so, how do we read it is the next thing to talk about. The way that we typically read it is if and only if. Is the way that we read that arrow. And, well, maybe we do the triple F thing real quick.
Triple.
So, when I have this statement, so let's look at this statement real quick. Because this statement and this statement are the exact same thing, right?
Mm-hmm.
So what does this statement say? This statement say,
A implies
Oh,
B.
A
and
only
B implies
if B.
this statement right here says B if A,
Right.
right?
Right.
And this statement right here says B only if A.
And
I always do it backwards.
No, you're right.
Oh,
Put your and in.
yeah. And then, and B only if A, right?
Right.
So then we say, combining these two together, we have a shorthand B if and only if A, and then finally we have our really shorthand, which is B if with two F's, A. Good?
Grand.
So P if Q and P only if Q is the same thing as if P then Q and if Q then P. Yeah, we get that, we get that, we got that. There's the symbol. And then grouping and parentheses. Okay, so you already, I even started using parentheses right here and you already intuitively understood what it means. Do the thing inside the parentheses first. Now, it can be kind of messy, I guess. Writing out parentheses all the time for every operation. I mean, imagine if I had to do, instead of something like, if every time we came across an operation like this, I had to explicitly write 8 times 5, but we're doing that first, plus 7, then we do that. Or even worse, what if this was 8 squared times 5? And I had to write that out with other parentheses right here with the square right there to make sure you understood, hey, you do the squaring first, then the multiplication, then you do the addition, right? And then what if that had been a negative 8 squared? Oh geez.
That's an important parentheses, okay?
Right, but the point is, it just starts blowing up with the parentheses. And so it's good to just have a precedence that you do, an order that you do these things in. So what takes highest precedence in logic is not. You do your nots first. So if I have not A and B, this does not mean not A and B, this means not A and B. Let me just write the order.
So pen dash.
Not, ors, and implies biconditional. Is the order that it goes in.
Nots, ors, and ands implies biconditional.
True. It's our order. So if I have not A and B, or, oh wait, and comes before or, sorry. And is like multiply, or is like plus. So if I have not A and B, or C and not D, then if we were to write this out a little bit more clear, what this is saying is not A and B, or C and not D.
Right.
And I don't know if the author explains it on this level. My separation of this actually just comes from programming. And then I also know that this operates a lot like times and this a lot like plus. So in programming, and takes precedence, and it makes sense for it too, because and acts a lot like multiply. Does that sound weird when I say that?
It looks right, okay?
We'll do a little tangent, just because I think that this is a full tangent, to make connections between arithmetic and
Programming.
in logic. So basically, if we were in discrete math, we'd be calling what we're doing here Boolean algebra. So a Boolean is something that's either true or false. That's what a Boolean is. So when you say a sentence is either true or false, it's a Boolean. That's what you're saying. It has a true value or it has a false value. It has a true or false value. And so there's only two values when you're doing Boolean algebra, true and false. If you're doing integer algebra, all the values are all the possible integers. When you did modular arithmetic, if we were doing mod 7, there were only 7 values, 0 through 6. So in Boolean algebra, there's only 2 values, true and false. Every variable is either true or false, and these are the only things that we can put things together with. And the operators we're going to use are not, and or, but actually we'll focus on these 2 operators, just and or. Now, so if I have some variable in this algebra, x, you know it's either true or false, right? Now, when we're talking about arithmetic, and I talk about the additive identity, what's the additive identity?
0.
0 is the additive identity. Why do we say 0 is the additive identity? Because x plus 0 is equal to x. Sorry. X plus 0 is equal to x. And the multiplicative identity is 1, because x times 1 is equal to x. And notice that when you take a number and you multiply by the additive identity, then you get the additive identity, 0. So now let's do the same thing, but with logic. If I take x and I OR it with false, that's always going to be whatever x was. If x is true, it's true. If x is false, it's false. If I take x and I AND it with true, it gives me x. If x is true, x in true is true. If x is false, x in true is false. Furthermore, if I take x and I AND it with the OR identity, it always gives me the OR identity itself.
Wait, take x and AND it.
So false is the OR identity, true is the AND identity. So you have your OR identity, your AND identity, and you have.
That is
So there's
so
some
cool.
similarities between them.
That is actually really cool.
Another thing that also happens to work is the distributive property, but we haven't gotten to that yet in logic. But we'll get there. Or how you did. Never mind.
It's a little weird.
Well, I guess I can just show you real quick. So if I were to do x times y plus z, then that's equal to x times y plus x times z. Similarly, if you do x and y or z, you would get x and y or x and z. It's messed up. Now, it tells you that there must be some abstractions that capture this information that you can study down the road. And there are, and you can. And you get to algebra. What we call abstract algebra. You've taken algebra courses, but if I ask you what's an algebra, you say, what do you mean? I say, exactly. Anyways, little tangent there. Can't remember what left down that. So grouping in parentheses, that's the precedence. He has some examples here. Examples are very spread out. Maybe we'll just look at them and make sure we understand. So if I say S implies H and U, where do the parentheses go? Do they go around this or around this?
And
The and.
What?
And before
Oh,
implied.
Let's rewrite it.
That's right.
Not and. I'm gonna start writing out and. Not and or implies logical equivalence. So, not A or B implies C is logically equivalent to D and F. Let's make sense of this one.
So not A.
So we have the not combined with the A.
And then
Are we going to put parentheses around this or this?
that's
A and
or.
B.
Did you
Parentheses
mean,
around A and
did you
B.
mean and or?
A or B.
That's an or.
Oh,
Yeah.
okay.
Just whatever I wrote here.
So they're around A or B?
Well,
So you're saying like this?
Yes.
well, no,
I think so.
because it's not A first,
Well, yeah.
That's
That's
not
a given.
and then D and F before technically.
Yes, but,
Oh, you're saying come over and do this real quick?
Yeah.
Okay, now we're done with that.
okay, now put, yes.
So you're saying around these two?
Yep.
And then you're saying like this?
Yep.
And then
And
around
then-
A.
Like that as well? Anyone out there bold enough to disagree?
What?
You don't see the one glaring problem with that?
1 second.
The C D1 looks weird.
Wait a minute.
No,
There's no problem here.
Yeah, that's the problem. You guys didn't mess up. Why can I yell at you? Alright, so I think you get the precedence. You know how to group them. He finally gets around to truth tables, but we already understand truth tables, right?
Oh, yeah. Like the back of my hand.
What's on the back of your hand?
Truth tables. That's why I understand. When does testing?
And then next, I think we're getting to atomic sentences. Oh, and then we can simplify these expressions the same way that we can simplify expressions that we're used to in algebra. So if I were to write out some big algebra expression, you would know how to simplify it.
Yes, sir.
We can also do the same thing with logic expressions. So someone want to read that expression to me?
N or G, parentheses around those two, and not N implies G implies N.
Applies
There's a parenthesis.
around this side.
And also
And
after
then
the
N to the N,
You're missing a parenthesis.
not N.
Not N, yeah.
Oh,
After
oh, duh, to finish that. Right. Okay, and then I can't remember which one. N, is it true or false?
N is true, G is false.
That's right. So N is true, G is false. So once we know the values for these, same thing if I had something like x plus y and negative
G
x.
is false.
Huh?
G is false.
G's fault.
Oh, thank you. Once we knew the values, then we can simplify these things. So let's go about simplifying this. So how do you simplify it? You just plug in the value same as you expect.
Yep.
So true or false is,
True.
so we have true and,
Not
let's see,
true.
not true is
False.
false. So we've got that implies, false implies true is,
True.
Fault.
false implies true is,
True.
Yeah, it's true.
true. Oh, I just get And then true and false is,
False.
false implies true.
It's
And
true.
so,
True.
Wow. That is actually so cool.
yeah, it's the same thing. When I give you a big algebra expression, that's really just a number represented in a really long way. This is just a Boolean represented in a really long way. Okay, so that's how you simplify it. Now let's talk about atomic sentences.
Wait.
Atomic sentences.
So we all understand what an atom is. What's an atom?
It's a very basic unit of the universe.
Well, it's built up out of quarks, right?
Yeah, it's built out of quarks, but
As a
you
proton,
understand some high-level definition you might give a 2-year-old is something along the lines of what Jacob said.
Small
It's
c.
the basic building blocks of the universe. Now, why did we call them atoms?
In the original Greek, it didn't mean undividable.
Yeah, indivisible, undividable. So there came a point where we, meaning the scientific community, thought that the atom was the smallest thing that there was, and that everything was built out of atoms. So that's what we mean by atomic. We mean, in some sense, fundamental, can't get smaller, this is as small as it gets. So we're going to talk about atomic sentences. Atomic sentences are basically sentences that do not contain sentential connectives. So if I say,
So they're basically just sentences that are true or false. And nothing else.
Jack likes Jill, and 2 + 2 = 5, then you'd say that there's 2 atomic sentences in there.
Yeah.
Jack likes Jill is one sentence statement, one atomic statement, and 2 + 2 = 5 is another atomic
and you're saying
statement.
it's as basic as it gets, or it's as reduced.
Right, we can't talk about the component sentences of Jack likes Jill.
Right.
That is as small, as condensed as that sentence gets. So let's get his definition exactly.
So does that include not as a sentential connective?
Yeah, not is a sentential connective.
So you can't have
Ooh.
an atomic sentence with not?
Not, let's see. Yeah, so for example, not is kind of not great. Remember how we typically write the not is we say it is not the case that, we've erased it. It is not the case that blah 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 blah. But the point is I could take something like, I'll just use not, I won't write it is not the case that blah 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 blah. We'll just say the sky is not blue. So there's our statement.
So you're
I could make A equal to the sky is blue,
so basically
and then not A now becomes my way of codifying that. So this was not an atomic sentence.
and the negation of that is an atomic sentence.
A is the atomic sentence, in this case it happens to be its negation. And then not A is our way of re-expressing that with its sentential connective. So let's write out his definition that he has there. It's going to be roughly along the lines of, so we'll say atomic sentence going to be
If it contains
a
no.
sentence
Sentential Connectives.
without any.
Sentential Connectives.
You could have just said no.
But that captures exactly what he's saying, right? He just doesn't give it very well as a definition, unfortunately.
It is what he gives, isn't it? Let us
It's
call
logically
something
equivalent to you. Let us call, my point is, for example, our Discrete Math book, one of my favorite books, I love it. Every time it gives a definition, it says definition, gives you the word, and then gives the definition right after.
Yeah.
He throws a definition in a sentence that you're just reading out of a paragraph.
Stem.
That is exactly how your calculus book was. That is annoying.
You're annoying.
Ooh,
No, that textbook was not great,
annoying calculus.
but it was also fast paced.
That's good. You got
We're gonna have a fun year.
Are we using the same textbook?
If I just have you and Emma, yeah.
Well, you talked for like an hour about how much you needed that textbook.
Yeah, the other one I could use is a lot slower, and it goes through it better for students who haven't been through a rigorous course before.
But this is a rigorous course.
You've done Discrete Math. She's done geometry at least.
Discrete Math is very rigorous.
She's done
It is in the sense that it is rigorous. You just go over a bunch of different topics. It's not as rigorous as it could be, but it starts out with here's the basic assumptions we're going to make,
Yeah.
and then gives you some definitions, starts building up. You just jump from topic to topic.
We should finish abstract algebra because I still want to do that.
Well, we could make abstract algebra the next course that I do as just a
That
course.
would be really cool.
Well, from logic to abstract algebra.
Is that at the end of the Discrete Math?
So Discrete Math, one of the things it does is it just like sticks your toe into a bunch of different fields of math.
Yeah.
And so you can take a class on number theory, but one of the chapters in the book is just number theory.
Mm-hmm.
And so it's just giving you a taste of it. So one of the chapters in the book is algebra,
I feel like we
giving you
started
just a
it,
taste
we
of
did
abstract algebra.
but-
No, we didn't do algebra, we debated it, we decided to do graph theory.
Oh yeah, and we only did a little bit of.
Is that considered like a whole field,
What?
graph theory? Or is it just like
I never knew of a graph theory class that was offered to me. I'm sure that it's a field, and we were often interested in it in different computer science classes. We would take pieces of it, but it's like we developed some of the theory as we went and used it. It's not that I ever took a class called graph theory, like I took a class called number theory. So I assume that such a course exists, but it's kind of like you never do a class called set theory. It's just set theory comes up in like 4 different math classes that you take.
Well, is there enough set theory to study to put an entire class together or not?
I haven't gone that far into set theory starting from the ground up, which is what this book hopefully does. So the first 8 chapters of this book are supposed to be logic, and then the next 4 chapters are supposed to be building up foundations in set theory from logic. That's
Because they would do
specifically the reason I
set theory
chose
first.
this textbook, is I wanted that exact thing. I wanted to start
That
with
is
logic
really cool.
and build your way up to your foundations of math.
Because then with set theory, you build up the natural numbers and you start doing.
Yeah, I know how to do that, so I can.
Well, that's what I'm saying. So with this, it starts from like the very bottom and moves up.
Right. So starting here, and I'm assuming that somewhere in this class we'll develop natural numbers. Make sure I haven't never gotten a phone call. Still going. Okay. That was a weird tangent about classes.
Sorry.
That's why I watch the YouTube videos.
For this.
Yeah, I didn't think people would care about that. I always debate editing that kind of stuff out. But my calculus class hated it when I didn't record everything.
I'm fine with you doing that. I remember going through discrete math and just like skipping a ton of stuff in between.
Yeah. Yeah. It's
Find it.
It's not like I'm setting up an online lecture series to teach people.
Yeah,
It's
otherwise
that.
you would.
We're just a bunch of people randomly getting together and going over logic. It's like recording a book club
Yeah.
to learn about some book. not the most efficient way to do it, but so that you have access to it after the fact, because I think
Right.
students found use in that. It's there. I wouldn't expect anyone to actually go through these lectures
You
to
could
learn
always put in the
material.
description of your YouTube video where they can skip more than nonsense.
I'm gonna go take the time to do that.
Yeah.
People can do that in the comments.
Here.
Who is this guy?
Yeah.
Stay on topic.
If you can find
We should start
if you can find
spamming
comments on my videos
Yeah.
that takes time to do that, then yeah, all I have is a description. Or I can just pin up, I can make the comment.
What you
at the
should
top.
do is when you label your lectures, label them by section as well. Because you always say chapter something, it'd be nice to know. Or you say lecture 1, lecture 2, lecture 3. But you could go lecture 1, Boolean Algebra, lecture 2, just the sections that you go through rather than.
Okay, Joe, if you're gonna add comments to all the videos.
Well, that doesn't help because then you have to, you still have to click on each one of them you're looking for. But like when I was studying for the final, I had to go back and.
No, I'm saying if you'll go do the comment, I'll copy paste the comment into the description.
I mean, the title.
He's saying going forward. Like,
Saying from the title, say lecture 1, this is the section.
yeah.
I can also add the title.
Yeah.
If you go through the work of doing that, I'll do what you want. I'm just not gonna go through the work of watching the lecture, seeing how far I got.
Well, it's the first thing you see in the lecture.
Yeah.
It's literally right on the board, the title.
Sometimes. And sometimes you get halfway through a lecture and finish the other half.
Oh, yeah.
Sure.
So I'd have to have the textbook next to me,
But yeah, you
look
start
at
out
it.
with
I'd have to see where I start, figure out where I end.
So all you do is when you post this lecture, you go lecture 2.
Yeah, but all you have to do is start at the beginning and then go to the end.
Or just watch the series start to finish, and then you don't care what I'm doing because you're following along.
Yeah, and I'm not gonna do that. I mean, I'm not
You
gonna
guys
care
know
anymore
double
because
speed.
there's no point
You
watching.
wanna watch it? You do it on double speed.
Always. If you're watching YouTube videos on anything but double speed,
It goes so fast, but it's good. That's what I do when I watch it.
it's great.
Yeah. He actually rather people that
I
just
don't
do
know
it
how
on
you keep
normal
up with
speed.
double speed.
Yeah.
Well, in discrete math,
I'll do
I was
1.5.
falling behind regular speed. So.
Trying to talk slower.
You can pause it and then write everything down.
Yeah, that's true.
It's nice.
Alright, well, let's continue. Okay, so the next topic, I didn't see a header for it, but the next topic we're going to get into is called tautologies. And hopefully, those of you who have done logic before remember a tautology.
Well, it was in the textbook.
Huh?
It was in the first 20 pages of the textbook.
Oh, in discrete math?
No,
In the
textbook you
calculus
sent
one
us.
that you sent.
It
Oh,
talks-
so even if you read the wrong textbook, you preparation for
That's
this.
happened
Yeah.
twice now.
It still talk. It talked about all this stuff.
I sent you guys the wrong textbook?
No, I'm saying we have twice come across terms from the other textbook.
Oh, that's the thing. Okay. Yeah, so a tautology. So what's a tautology?
It's basically a formula that gives you a true statement no matter what.
Yeah. That's exactly what it is. So when you take your atomic statements or your atomic sentences in any logical expression, it's going to always be true no matter what truth value you assign to those. So let's do an easy example. X or not X.
Will always be true.
Yeah, if you assign true to X, this statement's true. If you assign false to X, the statement's false.
True.
And it makes even more sense if you pick a statement and plug it in there. The sky is blue or the sky is not blue,
It's true.
Why can't it?
right?
Why can't it just be
The sky's blue or the sky's not blue.
right?
It's like the teacher gives you a problem, and you say the answer's 6 or the answer's not 6. Right. Tell me I'm wrong. So that's a tautology. I just realized I'm writing over here and I don't know that I lined up the camera to get all the way over there.
Barely.
Barely. Okay. We're okay. We're okay. So that is what a tautology is, and we're going to be very interested in tautologies throughout this class. So let's make sure it makes sense. Now, let me give you an example of something that's not a tautology real quick. x and y. So this is not a tautology,
Obviously.
even if x happens to be true and y happens to be true.
Obviously.
Well, you say obviously now, but there might come a point where I say something like, Donnie's a human being and he's alive is a tautology, right? It's always true.
Right.
No.
Right.
It's not always true.
Because you could die. You will.
Okay.
Yeah.
Well, let's think about another one.
So do you remember when you guys
Donnie's alive right now and he's a human being.
Okay.
That's a statement that's always true, right?
Right.
Yeah.
That is not a tautology, even though that statement happens to always be true. So the way you make sure it's a tautology is, first off,
Isn't
I'm
it?
going to say codify the sentence.
Isn't it where you plug in true or you plug in false? It always comes out true.
Right, so you look at the atomic statements. So when I said, Donnie's alive right now and he's a human being, you can codify that as A and B, right? And then that should help you see right out the door, oh, that's not tautology. It's possible for this thing to be false.
My guess is we're going to be codifying everything.
Well, that would make-
Every statement will codify.
Doesn't that help it make sense?
Yeah, it will help you make sense, but the point is, ultimately, this is still just a statement,
Yes.
Right.
right? And the goal here is to identify when it's a tautology versus when it's just always true.
What's the opposite of tautology? Because and not is going to be always false.
Right, so there's statements that are always false. It's just in math, we're interested in statements that are always true. So when you prove something's true in math, you show that A implies B is tautologically true, or in other words, the implication A implies B is a tautology. So you're not interested in the case where you prove something's always false, you're interested in the case where you show it's always true. So we don't have a word for the case where, well, there might be a word, but it's not one we're
I
interested in.
understand why.
Okay, so he says it is. So let's read exactly what he says a tautology is. We'll probably write it up since this is crucial for the rest of the course. You see, I'll just read it and go write it all. Oh, you just spell it wrong. Tautology.
Yeah.
Tautology. Right, it's another one of those definitions in a sentence, so we gotta rip out the definition. A compound sentence, okay, we didn't say compound sentence, what a compound sentence is, and he must have given that up higher. What's compound sentence?
Two sentences that
It's
are
two
connected by
concepts
one
or
word.
conjunction.
Doesn't have to be two sentences. But if it's composed of multiple atomic sentences, then it's a compound sentence. So a tautology is going to be a type of compound sentence, meaning it has to have at least two atomic sentences in there. So let's start writing this out. A compound sentence.
What?
Just gonna shut it all the way around.
Or is it your creepy star?
So let's see, a compound sentence that is always true, independent of the truth values of its component atomic sentences. Compound sentence that is always true, independent. Is that an A? Or an E?
No, D.
D.
And D.
Wow, I missed my D.
Yeah.
I got thinking of the next letter.
Yeah,
And then E and T?
I think so. Yeah, it's a lot of E's.
Alright. That is always true, independent of the truth values
Component.
of its
Atomic sentence.
atomic sentences. Okay, that's what tautology is. And notice that tautology is very much captured in the form of the sentence, not the component atomic sentences. It's in the not something or something. You know, whatever you put in right here, if you put in the same thing twice, I should say. But this is just kind of telling you the shape, the form that the sentence would take on. Not the sky is blue or the sky is blue is always a tautology.
Has to be that way? Or are we always going to see it that way?
A tautology is captured that way. In other words, it's almost exactly what you were saying before. It will be a lot more obvious when you codify the statement. So don't think about, is a statement always true? Think about when you codify it, ignore the statements it was associated with and just codify it. And then see. And remember when you codify it to always codify the same statement to the same variable.
What does codify mean?
That I told you that's the verbiage I'm going to use. Your author doesn't say that. I'm not sure what he says. That's what I'm going to say for when you represent a statement with a letter. And when you represent your sentential connectives with our logical operators that we have here.
Okay.
So, Jack likes Jill and 2 + 2 = 5. Here's how I codified that.
Oh. Okay.
That's how I'm using that word. Because I'm going to say it out loud. So, take it, codify it, then it should be a lot more obvious. I won't say obvious. It should be a lot more obvious or a lot easier to determine whether or not it is a tautology. Because it has nothing to do with the actual statements being used. That's the weird part when you first come across this. Make sense?
I still don't see. I see the definition, but I don't see it in an equation or in a sentence.
So, let me give you an example of something that's not a tautology, that you might be tempted to say is a tautology. 1 + 1 = 2, and 2 + 2 = 4. You might think that's always true, right? Therefore it's a tautology. No, it's not a tautology. Codify it, make this x and y. Is x and y always true? No. So this is not a tautology. Even though the statement happens to always be true. It's a nice accident.
So tautology is when you codify it, then it has to be true for every case.
Whether you put true
Yes. It doesn't matter. It does not depend on the truth or falsity of x and y. The fact that 1 + 1 = 2 is true, irrelevant for when you're talking about whether or not it's a tautology. Whether or not this is true, irrelevant. So, a compound sentence, meaning it has multiple atomic sentences, that is always true independent of the truth values of its component atomic sentences.
So I don't see any sentences that be atomic.
That'd be atomic. This was atomic.
Or sorry,
A tautology.
tautology.
Here's a tautology. 1 + 1 = 2, or 1 + 1 is not 2. Let's codify that. What do we get? We get x or not x, right?
Okay.
That's always true. If x is false, that statement's true. If x is true, that statement's true.
Okay.
There's no way that you can assign x values in there to make it false. Let's look at another one with a couple more variables in it. Let's see. What if I did something like, if 1 + 1 = 2 and 1 + 1 is not equal to 2, then I don't know. Then the TV is on. Okay. So is this a tautology? Let's codify it. 1 + 1 = 2. We'll represent with
True.
no.
Oh, right. A.
A, sure. And
Not
not A implies, because this is an if-then statement, B.
So that is a tautology.
So this is a tautology.
Because false implies.
Because this is always false. False implies anything is always true.
Right.
This is a tautology.
false implies anything is always true.
Yeah.
Yeah.
We know that. Well, that's how.
Oh yeah.
False implies true is true. False implies false is true. Those are the only things that can apply. You can either apply true or false. So when we say anything, we're only talking about two cases, true or false. So if 1 plus 1 is 2 and 1 plus 1 is not 2, then the TV is on.
It's such nonsense.
True, always true.
Obviously.
Not only is it true, it's a tautology. I could replace this with any statement I want, as long as I replace this with the not of it,
Yeah.
and replace this with any statement I want, it's always true. Right? So once I codify it like this, plug in any sentence you want for A and B. Any sentences in the world you can think of, and it will still be a true statement. That's what a tautology is. Is that clicking a little bit better?
When is the tautology used?
From here on out, we're going to be using tautologies all the time. Basically, all the implications that we're going to care about from here on out are tautological implications. Implications that are always true, like this implication is always true.
It just seems ridiculous, I'm sure,
Mhm.
but.
It just seems ridiculous, you're sure?
Can you give us like an example of context where we are going to use it?
Well, he was saying
Theorems. Every theorem is an if-then statement. And when you prove a theorem, you show that it is a tautology. That's what you're doing.
Great.
by proof.
Yeah, so we'll get into proofs later, and the proofs that we did in math classes. You think about the most well-done proof you can think about that you've ever done in one of your math classes. In logic, we call that an informal proof. We say, it was pretty informal. You didn't rigorously prove it.
What is it? What do you mean?
Well, we'll get into a logical proof,
Oh.
where we follow out every step. We say exactly what rule we're using and how the previous statements imply the following statement. Because basically all we're going to care about is premises, tautological implications, and then conditional statements. And you're used to conditional proofs. You've done it all the time. I say prove something along the lines of, let's see one example. So premise. 2 plus 3 equals 5. This is a premise. We're not going to prove it. You're going to assume that this is true. Then I say prove. So prove, here's something along the lines of something you've done 100 times, but way oversimplified. Prove if x equals 2, then x plus 3 equals 5. Right? So you have your premise. I didn't give you another implication to use. This was too oversimplifying because I also needed to throw in just a theorem.
You could use the even out odd one from the beginning of it.
Well, you already understand the theorem, so the only one I need to help you understand after this is the conditional. So you can use your premises, you can use your theorems, and then you can have I'm not sure exactly how he's going to say it in the book, but then you can have your conditional premise and conclusions. So we'll just use it real quick here. How do you typically do a proof like this?
You would.
You start out saying let 2 plus 3 equals 5.
No, you start out with something along the lines of let or assume x equals 2.
Right.
Oh.
That's how you start it.
If
Here was the only thing we were assuming.
Okay.
And then
Now we're conditionally assuming x equals 2.
Well, don't you have to say assume 2 plus 3 equals 5?
No, that's a premise.
That is your premise.
It's a premise that we're using because it's already something that we have proved in the past. So now we get used as a premise from here on
You don't
out.
have to state that.
Yeah, I mean, when you did your proofs in discrete math, if you were doing a proof later in the chapter, you could use all the pre-existing stuff as a premise if you
Right,
wanted to
right.
in theorems.
But you didn't have to explain it. In
This
the-
is just a paragraph.
So we're just saying here's a premise that we're going to allow us to operate on.
You know,
I mean, if you want to go all the way back, it goes back to axioms or your initial premises.
Right.
You have your axioms and whatever that you're talking about. So here's an axiom. 2 plus 3 equals 5.
Mhm.
Now we're going to say prove if x equals 2, then x plus 3 equals 5. So we assume x equals 2. Now this does not mean from here on out for all of time x equals 2.
For this proof.
It's only for this proof we're letting x equal 2, so it's a conditional premise, and then we're going to come to some conclusion, x plus 3 equals 5. So assume x equals 2, then x plus 3 is equal to 2 plus 3 is equal to 5. Or maybe I'd say then x plus 3 is equal to 2 plus 3, then x plus 3 is equal to 5. Now, what did we show when this is all said and done?
You showed what you originally tried to prove.
We showed that if x equals 2, then x plus 3 equals 5, with this premise already given. Notice this only works if this premise is given.
No.
No.
If 2 plus 3 does not equal 5, I cannot do this proof.
Oh, right.
Okay.
I have to assume my one premise here.
We
This
have
is the only thing I
Take away
assume.
everything you know.
That's why I said way oversimplified example. All we're going to use is the fact that 2 plus 3 equals 5. That's our whole premise
Okay.
from here on out. Now we're going to show if x equals 2, then x plus 3 equals 5.
Right. Yeah, this makes a lot more sense.
Okay.
Okay?
Okay.
So we go out and we do the proof.
Right.
So what did we show? We showed, if I can call this statement A, we showed that A implies, parenthesis, call this statement x equals 2b. B is
Dude, it's all one big.
x equals 2, and C is x plus 3 equals 5.
Yeah.
That's a C. So I just basically showed A implies, B implies C.
Okay.
This implication I would show is always true given this premise.
Okay.
This becomes a tautological implication.
Given that A is true.
Well, this.
A,
You see this implication here?
A can't be false, so
The outer premise.
How is that?
A can't be false. You said
But B implies C is true.
Tautology.
If
says
A is
any-
false, then it's already true. So now we only care about the case where A is true.
Right, so if B is false.
And A being true makes this true.
No. Well, with
That's
your
what we
proof-
just showed
with
here.
your proof, but like,
We just really showed if A is false, we already know this is true.
right.
If A is true, this is true.
Why?
That's what we proved. All we assume for this proof is that 2 plus 3
So-
equals 5.
What do you mean if A is false, then that's
Yeah.
true?
Because
Yeah, it's
look
an
at our
implication.
False implies
C equals
anything.
truth table.
False implies true is true. False implies false is true.
Right.
Okay.
So if it happens to be true that 2 plus 3 is not equal to 5, if this statement happens to be false, this implication is still true. Right?
Yeah.
And we just barely showed the more interesting case, the case we care about, the harder case.
So basically.
What about when A is true? Well, and then we have our proof, this is also true.
So when you're proving something, you're basically saying, in this case, it is a tautology.
So, no, A implies, B implies C. Oh, now I see what you're saying.
Yeah. Because you can't substitute B with false.
Right.
It has to be true.
Well,
Yeah,
B
you
is
were
true on
right.
the premise that 2 plus 3 equals 5, right?
You can't substitute C
Or
with
so-
Oh,
false.
wait. No, Levi, I think. Okay. In your proof, though, if always has to be true, right?
Yeah, your premise for B implies
If
C is
X is true,
Right, you're working with the assumption that X is 2.
prove that if, there's no way to take the statements out from that.
There's no way you can say C is false. There's no way you can say B is false. And that's why it can't be tautology, because if you plug those in, then it doesn't matter.
Yeah, I'm missing a piece in my thinking. The because we're not showing that a statement is a tautology.
We're showing that it's true, right?
We're showing that a particular statement is always true.
Right.
So we're going to say this particular statement tautologically implies this statement. And how are we going to make sense of that with that as our definition as a compound sentence?
You could.
Maybe there's some notion of dependence that we're missing.
You want to try using the
Because the truth of B depends on A. Or the truth of C.
you could modify your definition.
Well, that's the definition it gives. You can't change our definition.
The
So I'll have
definition of
to
that,
think about it more.
the calculus textbook you sent us was a formula using logical statements that is always true is called a tautology.
Right. And we haven't gone to formula yet in this class, but a sentence is a type of formula. And maybe we're cheating when we're trying to replace, when we're trying to get rid of the structure from the statement by getting rid of the plus signs. So maybe I'm kind of cheating when I codify this like this and this like this. Maybe I needed to just use word statements there. Because we'll talk about formulas in this book, and the way that he talks about a sentence is a particular type of formula.
Should we read it using words instead of?
Well, I'm just saying, maybe I'm cheating, just writing that as an A. Maybe there's structure I cheated, structure I removed from this, just writing it as an A.
What do you mean? You're saying it should be more than A?
Yeah, maybe
Like
this is
A
the same
and
thing
B.
as A is equivalent to B
Right.
is what? If we were to get it down to its atomic pieces.
Right.
And so when it comes to a math formula, I might be oversimplifying.
Okay.
So I think we got rid of structure here, and all we can think about is,
Well, that doesn't make sense. 1 plus 1 is in the statement. There's no verb.
no, it's not. Yeah, I don't know. Have to think about it more. But we'll get to it.
Okay.
Because this does have to be a tautology.
Is that what proofs are? Proofs are showing that something's a tautology?
That's impossible for it to be false.
Right. So my it's impossible for it to be false, but that is assuming that something's true. You can't manipulate. You can't manipulate it and say that if this is false, then it's true. Well, I guess you can't. Can you?
Well, we know an example of one right out the door. X or not X. It's impossible for that to be false.
Right.
So that's a tautology.
How do you can
That's
you use
circular
like a
logic,
basic?
though.
No, that's what you just tried to
Yeah, I just tried to come up with a proof on the fly,
do. Yeah.
and I'm sure that there's some detail that we're going to get to that will help clear all this up.
Right.
So, shouldn't try skipping to what's probably like chapter 4 stuff.
Probably.
All right. Anyways, so there's tautology. P or not P. Let's see. True or false? That is true, and hence a tautology. Derived truth tables are more convenient. Okay, so one way we can always check if something's a tautology is we write out the entire truth table for the expression, and if it's always true in the resulting column that has the tautology that we were analyzing, then it's a tautology. So
Your implication one.
yeah, let's write out the truth table for this one real quick, just to see it in action. We already know it's a tautology, but let's just see the truth table that I was talking about. So we only have 2 atomic sentences here, A and B, right?
Yes.
And since we have 2 atomic sentences,
You have 3.
then we're going to have 4 rows. True, true,
Not B.
false, false,
It's A and not A.
false,
Implies B.
true, false. So yeah, ultimately the thing that we're trying to write out is
Oh yeah.
A and not A implies B, right?
Mm-hmm.
So let's write out A and not A real quick. And then we'll write out, that should be all we need, right? So we'll just do A and not A here. So true and false is
False.
false.
True and true is true.
True and false is
True and true, right?
true and false is
Well,
Oh,
and
sorry,
false.
yes, you're right.
A and not A, false.
False.
False false and true is,
False.
false and true is.
False.
Finally, false implies anything is always true, 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 true. That was a very interesting one. Let's see if he gives us a more interesting tautology. I think if you switch the or to the other side, that should become a tautology. So he's saying P or Q implies P is not a tautology, because there's one case there where it's false, right? But I think if we switch it the other way, then that will be a tautology. So another tautology would
P
be,
implies P or Q.
yeah. So I think P, no, that's not one. Never mind. Let's-
Hey, look, there's a formal definition.
Oh, there we go. Oh, so I think that this was just a intuitive definition.
Yeah.
So let's read through his formal definition. I don't want to write out that nasty thing. A sentence is a tautology if and only if the result of replacing any of its component atomic sentences in all occurrences by other atomic sentences is always a true sentence. Oh, that's pretty close to the same thing.
Mhm.
So that doesn't change it much. And then the author makes a note. So here we only had 4 rows in our truth table, or in the one that we just did, because we only were dealing with 2 variables.
Right.
If I were dealing with 3 variables, I'd have to have 8 rows in my truth table. If I were dealing with 4 variables, I'd have to have 16 rows in my truth table. If I were dealing with 5 rows, I'd have to have 32. If I were dealing with 10 variables, how many rows do I have to have?
1028.
Almost.
How did you do that?
It's just 2 to the power of 10. I don't have that memorized.
1024.
Good job. 1024. So we'd have to have, if we were just looking at some expression that had 10 variables in it, and we wanted to determine is this a tautology, then we would have to write out 1024 rows and fill out that table. And there's a very good chance that we would make a mistake. So while you can always determine if something is a tautology by doing the truth table, it becomes impractical.
So technically,
For
you could though.
Bigger.
Could you get a computer program to do it maybe?
Sure.
Yeah.
Yeah, that won't make mistakes. This book is written in 1957.
Right.
So keep that in mind. So he doesn't know about computers.
Who's popular?
What was popular back then?
1957?
War.
That's 3 years after World War II. So
He's the first author I've ever seen write out the word nincompoop.
Oh, that's great.
And then what's the word he uses all the time? Idiom. He says the word idiom all the time.
That's such a cool word to hear.
An idiom.
I don't know.
So
what
he
it is.
talks it.
Yeah,
Oh,
like idiom.
no. So it's important you know what an idiom is if you don't understand what the word means. What's a common idiom? Who knows a common idiom?
The duck's feathers fall off.
No,
the
that's-
water off the duck's back.
Like water off a duck's back. So like water off a duck's back is an idiom because when someone says it's like water off a duck's back,
Right.
well that's more of an analogy than an idiom.
Well, that's still an idiom.
Yeah, kind of. The point of an idiom is it doesn't the meaning doesn't derive from the actual words used, but more the usage of the words. So raining cats and dogs.
Yeah.
Like if you were studying the English language and you never heard someone say raining cats and dogs before, and then you came across a book and someone says it's raining cats and dogs, you'd be like, what?
I still.
Or bite the bullet.
Yeah.
And I say, James, just bite the bullet. I'm not asking you to go chew on a bullet. When I say it's raining cats and dogs, I don't literally mean it's raining cats and dogs. So it's a grouping of words that gets its meaning more from usage, from the context, than from the individual words themselves. And so we talked about the statement, let's see, I can't remember exactly how I did it, but it was something like, John, oh well, misspelled John,
That's what
likes Jane, or we'll say dates, I think is what I said.
Yeah.
Dates Jane only if Jill is mad at him.
I think it's the other way around.
Yeah, actually.
Let's say it's Jack,
Yeah, Jack, not John.
James.
Whatever. The point is, when you read this statement, then how are you reading it? You're reading it that if Jill is mad at John, then he goes and he dates Jane.
Right.
You don't read it as if he dates Jane, then Jill is mad at him.
Which is logical.
So we would say that this is idiomatically incorrect
Right. Because
because it didn't follow the correct usage of only if.
That doesn't
Okay, I
make a
think
lot of
I'm
sense. I mean, it makes sense, but like, that's a weird way to use it. I've never heard
Yeah.
Yeah, why would you use
I think
that?
I'm understanding.
Idiom.
well, he's pretty much saying because we understand.
Yeah, this
people
has-
date and someone's mad. Like there's so
I
much.
get what you're saying.
This is an idiom
I
in
understand.
mathematics and in science.
Yeah.
It has a very particular meaning, and it's not one that you can get from just the words themselves.
Okay.
Isn't it?
You could come to that conclusion,
Isn't
but you
it?
could also come to a different conclusion based off of the way the words are used in every
Oh,
speech.
he's saying
Right.
this is
So
not
that's
idiomatic.
it's an idiom.
This is not idiomatically correct usage of only if,
Right. Given the. Okay.
because it has an understood meaning in the context of
in a
math
mathematical context.
and science.
right.
Yeah. So in the context of math and science, this has a proper usage. This means a specific thing. So it operates like an idiom, the same way biting a bullet does. What's the other word that he uses like crazy? Piecemeal. Piecemeal. All the time. Piecemeal. Yeah.
Why does he use that?
You talked about you can use your premises piecemeal.
What does piecemeal mean?
You can take it one at a time, not necessarily a particular order. Don't have to do it all in one go.
Oh,
You
think
can use your
about it.
premises piecemeal. Yeah.
Never heard that.
Yeah, it's an older book, so
It's not that old.
57.
Yeah, and they're like relatively.
60
Adam, you're not right, this
But we know people that would talk like that. Like there's people that we would talk to that talk like that. That's not that old.
Yeah.
There's very few people you talk to who were getting a formal education 63 years ago. People typically reading this textbook were 20 63 years ago. They're now 83.
Okay.
Furthermore, the author of the textbook was even older when he wrote it. So speaking to him, he's probably talking to someone who's like 126 now.
Okay.
Grandpa.
There's a big gap. 57. Oh, that's a while ago. And you can definitely feel it in the speech of the text. Because the author, occasionally he uses a word that you don't think is very awkward compared to his other usages. And he apologizes for not using a typically used word, but he felt he had to.
That's funny.
Interesting.
So, yeah, you can definitely tell it's an older textbook by reading the textbook.
Anyway, what is this getting to though?
Where is this whole section going? Where is it leading somewhere, or are we just?
The point of this chapter is to get you comfortable with sentential connectives.
Okay,
That's
what?
connecting two, true or false.
It's getting you comfortable with not, and, or, if, then, in a biconditional.
So
That's
why
it.
are we learning what tautologies?
Because they involve those.
Oh, yeah, it's going to throw tautology in there.
Just because you need to know
Yeah, it's like our math textbook kind of does the same thing. At the end of some section it says, and by the way, here's a tautology, here's how it's useful, here's vacuously true, and here's how it's useful. I mean, we'll use it much more later.
it. Right.
That is just a table for how he suggests to determine the values of these things. I don't write the
Wait a
table.
minute, wait.
I ignore it altogether.
Why is there truth values for or and?
Yes.
Right, so you'll have to read through what he's doing there, but he's ORing those together and putting that under the OR. He's evaluating it as he goes down, so rather than doing what we do in algebra where we just rewrite the expression simplified,
He's just kind of mixing it.
he's making a big old table, which I don't think is a good way to do it. I don't recommend doing it that way. And I'm not going to bother trying to explain his thinking in doing it. You can read through his explaining it all. Alright, finally it should be noted that a sentence is if a sentence is a tautology, we may substitute any, we already said that. Oh, and the result will still be a tautology, of course. That's fine. So let's read these two things, I guess. A statement which is not a tautology may become one upon the substitution of compound sentences for atomic sentences. Let me make sure I understand that right. A statement which is not a tautology may become one upon the substitution of compound sentences for atomic sentences, or substitution of the same atomic sentence for distinct atomic sentences in the original statement.
Good thoughts.
Yeah.
That's so.
I understand what the first part of that's saying. Or substitution of the same atomic sentence for distinct, thank you, atomic sentences in the original statement. Okay. So, in other words, how can I make a tautology? Well, if I had something like A or not B, if I replace that with another A instead, it then becomes a tautology.
Okay.
So that's one of the things he's saying. And then the other thing he's saying is we can replace we can replace compound sentences with atomic sentences to turn it into tautologies.
You could just use A and B.
So it seems like we should do the reverse.
It is the
If it's a tautology, if you get rid of the atomic, is he saying get rid of the atomic with a compound?
Yeah, it is.
Oh, a statement which is not a tautology may become one upon the substitution of compound sentences for atomic sentences. No, he's saying you get rid of a compound and you put in an atomic.
No, he's
Get
saying
rid of
you
the
get.
atomic and put in a compound.
Oh, you're right. Okay, now I know you're right. Thank you. Okay, that one makes more sense.
Because then A and B becomes A and B and B.
So let's think about a case of it. So P implies Q is not a tautology, but we could replace this with the compound sentence P and not P implies Q. And now it is a tautology.
Because it's false.
So we replaced, he's not saying every time you do it, he's saying it's possible to take an atomic sentence, replace it with a compound sentence, and turn the whole thing into a tautology. Is that making sense?
Mm-hmm.
This wasn't a tautology, this now is a tautology.
Yes, sir.
I don't know, I'm trying to read you guys. Is anyone even a little bit confused by that?
I think it's total sense.
This isn't a tautology. P implies Q is not always true. This statement is always true. Why is this statement always true?
Because that's
Because this is always false.
oh,
yeah.
and I
Yeah.
was reading it as or.
Oh, okay. So let's look at why this right here is always a tautology. Because P and not P is always false.
Yeah.
False implies Q. False implies true is true. False implies false is true.
Yeah,
So we turned it into a tautology.
Mm-hmm.
okay.
So as we were saying there, so the first one makes sense. A statement which is a tautology remains so when any sentences are substituted for its component atomic sentences in all occurrences.
He's just saying.
That's
Right.
basically the definition of a tautology.
Yeah, so you can take an atomic sentence, replace it with another one, and it's still a tautology. So let's write one out that we knew was a tautology. We'll follow this right here. The sky is blue.
And sky is blue and this sky is not blue.
If the sky is blue, and the sky is not blue, then what?
Your brain looks blue.
Pigs can fly.
Okey-dokey.
There's a statement that's always true.
It's true.
Yeah, there's a statement that's always true. It's a tautology. Furthermore, if I replace the sky is blue with whatever, let's rewrite the sentence now, but let's replace its atomic sentences with other sentences. What should we replace the sky is blue with?
The sky is black.
Oh.
Getting creative there.
I'm a little racist.
If cows eat dogs.
They get bloated.
Now, here's what he's saying. Here's what he's saying in this other part. So he said, a statement, which is a tautology, remains so when any sentences are substituted for its component atomic sentences in all occurrences.
Yeah.
So what that means is, if I'm going to replace the sky is blue with cows eat dogs, I have to also replace the sky is not blue with and cows do not eat dogs.
Then
Then
Donnie is a dragon.
Donnie is a dragon. There's another statement that's always true.
So what's your point?
I am writing out an example of what the second one is saying. My point is to explain the textbook. That's my point.
No, that's all makes sense.
Yeah.
A statement which is a tautology remains so when any sentences are substituted for its component atomic sentences in all
Didn't
occurrences.
we already go through that? We explained that.
We did it with true false.
Yeah, we did with truth false values. He's not getting to Boolean values right now. He's just saying with sentences in general.
It's the same thing.
Yes, it is.
Yes, it is the same thing. We're still just talking about tautologies. We haven't changed topics. It's just lots of examples, make it very clear. Okay. Finally, we get to tautological implications and equivalences. A tautological implication is an implication that's always true. The tautology that we happen to be using was a tautological implication. Okay? It's just a regular implication. A regular A implies B, but one that's always true. Okay? Tautological equivalence is the exact same thing. It's an equivalence where the equivalence is always true.
What's the equivalent?
Can you give an example?
An example? Well, sure, we could use.
Well, what does equivalence mean?
So we could take.
Oh, okay. It's basically if and only if, right?
Yeah, when an if and only if is always true.
Okay.
So let's take one tautological implication. So we'll use one that we've been using. Not A and B, or not A and A,
Or
implies. So false implies, and then I'm gonna have to have something that's always false over here as well. So if I want
that's
to be,
not. That's
let's do this.
It's got to be true, doesn't it?
No, I could do false implies false, and then the
Right.
what's it called?
And equivalence.
Uh,
It's true. If and only.
False and false.
or what?
Converse.
Thank you. The converse of that would
Yeah.
also be false implies false, but I can also make it true implies true.
Well, I thought it was tautology had to be true.
If I made false implies false, it's true.
Mm-hmm.
False implies false is true.
Okay. Yeah, I see your point.
Okay. But we can do true.
But it's all.
So not A or A.
No, not A and A.
I would pick one that's always true.
Oh.
So So all of this implies, we'll get real messy with it, not B and B implies C.
Okay. Yeah.
So now if I take, so this over here is always
True.
true. This over here is
True.
true.
And then you
So
just-
now I can replace this with an equivalent sign.
Dude, if you like.
This implies this is always true, this implies this is always true. Therefore, if we do the equivalence on this, it's always true.
It's actually cool. Someone walked into the room and saw that we were able to drive that just because of not, literally not, or if and only if and.
English,
Okay, so that's intuition for what these are. Let's get into exactly what's said. A sentence P is said to tautologically imply a sentence Q if and only if the conditional P implies Q is a tautology. So I think that's exactly what I said. Does that make perfect sense to everyone here?
No.
You understand what an implication is?
Yes.
We say P tautologically implies Q if and only if this is a tautology.
Okay.
In this case, it's not, but
But now just
if we make this an arrow, then this implication is always true, right? So this is, we would say if we call the thing in parentheses over here P and the thing in parentheses over here Q, this sentence P, this sentence Q, then in this case, P tautologically implies Q.
Q. Okay.
True in every case.
True in every case. Thus, a sentence, Locke was a bachelor and Newton never married, tautologically implies Newton never married.
Okay. I guess.
Mm-hmm.
Yeah.
So let's look at that one. He's saying, let me read it one more time. The sentence, Locke was a bachelor, we'll do L, and Newton never married, implies Newton never married. He's saying this is a tautology. Right?
Right, because n is always false. No.
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 This one we might actually need truth table for, so let's write it out. So we have L, N, and then what? Shoot, was it L and N?
Yeah.
Implies.
And then we'll finally do L and N implies N. Shouldn't matter which one.
That can't be true.
There we go. So here's what's going to be our tautology. So true, true, false, false, true, false, true, false.
And then
So if they're
false.
both true, this is true. Otherwise, false, false, false. Now, true implies true is
True.
true. And then false implies anything
That's true.
is always true.
That's obvious.
Okay, that does. What a joke.
Huh?
False
One
implies anything.
What a joke.
Yeah.
That's true though.
I'm hilarious.
Oh. What?
I didn't
Yeah.
expect that.
That seems like poor logic. Like that seems like. Read the sentence.
No, it makes sense. It makes
Locke
perfect
was a
sense.
bachelor and Newton never married. Tautologically implies Newton never married.
Okay,
Yeah.
that makes sense.
Here's the way that you could say that, and then say the statement's always true. If Locke was a bachelor and Newton never married, then Newton never married.
Yeah, it makes perfect sense.
Well done.
If Locke was a bachelor.
And Newton never married, then Newton never married.
Because
Because what?
he never married. Because you're pretty much just saying it over again.
It's just giving your premise, basically.
If I'm holding a marker and Jacob's in this room, then Jacob's in this room.
Yeah, see? You're just double.
That's always true.
Right.
Yeah.
True, true. Makes sense.
Exactly.
Okay.
Could I just throw around
The point is, the fact that it's a tautology is in the structure,
Right.
not necessarily the words being
I'm
said.
trying to see where this is going. It's like,
Yeah, I know.
at this point, it's like, why are we doing this?
We're gonna use this back to build anything.
Well, I already tried to help you where we're going with it, because the only implications we're going to care about are going to be tautological implications. This example may falsely encourage the idea.
Exactly what we were just
Yeah.
saying.
This example may falsely encourage the idea that the notion of tautological implication is trivial, as we shall see in the next chapter. So, you won't have to think that it's trivial for long.
Noise.
Oh, so one more point that he's going to point out, so you don't have to ever write the last column in here. He's going to kind of do, so he's only ever going to write out the truth tables this far. He's going to say, all we need to check is,
For
if
all truths.
when the antecedent is true, is the consequent true?
Which is the simple table you can do.
Which is what we always do in math proofs. We say, if this is true, is the consequent true?
Right.
We don't ever worry about showing when it's false, because we don't care about those cases.
Right.
False implies anything is always true, so all we care about is when the if part is true, is the conclusion still true?
Right.
To prove it's always true. So, let's continue. Oh, so that's what I was saying. So all we ask ourselves is, okay, so the only case where the premise is true, remember this was a statement, I erased what the statement looked like. The statement we were looking at was
L and
L
and N implies N.
L and N implies N. So all we care about is when the antecedent is true, is the consequent true?
Right.
So we look at when it's true. Was the consequent true? Yes. Okay, then it's a tautology. We don't need to check the false cases
Because they are obviously true.
because false always implies anything is true. So we just need to say when it's true, does it imply true?
Right.
Make sense?
Yeah.
So that's why his truth table, he did the same truth table we did. He just cut out the last part because we're not going to write the last part anymore. Good? Okay. Ba-ba-da-ba-da. So, not sure what he was showing here. This means the sentence A and not L is the same thing as not A or L. Okay, so now he's doing the tautological equivalence. So we move from the implication to the equivalence. So he's saying that not A or not B. Oh wait,
Logically.
I think it's just a B, right?
Yeah.
Because only one is not the other. So he's saying this is tautologically equivalent to, let's see, it's going to be A and not B, right? A and not B. So he's saying this is tautologically equivalent to that. Or in other words, when we write out the truth table for this, it's going to be a tautology. Okay? Once again, on the truth table, he's not going to bother out writing the column that shows this. He's just going to write out the column that shows this, write out the column that shows this, and show that they're always the same.
Right.
Therefore, if you were to write out this column, it would always be true.
Right.
Does that make sense? What column we're skipping?
Yeah.
Good? No? Let's write it out then. Okay, so let's write this out and show that this is a tautological equivalence.
We don't need to write it out, we just need to look at it.
We'll write it out. It helps to rethink through all this stuff over and over again. So we're going to have A, we're going to have B, we're going to have
Not A.
not A,
Not B.
we're going to have not B,
Yeah, not A and B.
we're going to have A and not B. Well, we'll do that one last. We're going to have not A or B,
Oh yeah.
and then we're going to have not A or B. And then we're going to have
The whole
this one, A and not B. And then finally we're going to have
The implications.
the whole
Yeah.
thing, that right there. Okay?
Well,
we don't need to do that because we wrote out the truth table for that already, which I guess I just erased. We showed that.
Yeah.
So we'll write out the truth table for just this operator real quick on the side here. A, B, and then A is equivalent to B. So we can have true, true, false, false. We can have true, false, true, false. And we said that A is equivalent to B only when they're both true or both false. So it's true in this case, and false in any other cases. And then we showed in the table I erased that this is the same thing as showing that A implies B and B implies A. So if we were to write out the big thing for A implies B and B implies A, it has the exact same truth values as this. Okay. So let's start. So that marker's kind of. So we can have true, true, false, false, true, false, true, false. This is not A. So if A is true, not A is false. If A is true, not A is false. If A is false, true. If A is false, true. This column's not B. So it's going to be false, true, false, true. Everyone good with that? Okay, now we're doing not A or B. So we're ORing together these two columns. So true or false is
True.
False or false is
False. True. True.
true, true. Everyone good with that?
And then we're gonna not that false.
Okay, now we're gonna not this column. So it's just gonna be false, true, false, false. Everyone good with that? Okay, so we did the left-hand side. Now we're gonna do the right-hand side. This is A and not B. So we're doing A and not B. So true and false is
False.
false.
True.
True and false is
True.
oh, it's
True.
A and not B. True and true is
True.
true.
And
False and false is false and true is
False.
okay.
The same.
So notice that this column has the same thing as this column.
Yep.
So if I were to write that whole thing out, put it right here on the truth table and start filling it out, is this the same as this? Yes. 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 So this is a tautology because this and this are the same thing.
Yeah.
So that's what we mean by these are logically equivalent. We mean in some way they're the same thing.
Yeah.
If this is tautologically equivalent to this, then that means they're somehow really the same thing.
How
It's
do
two
you
different
read
ways of
this
writing the same
example?
thing. Huh?
How do you read this example?
How do I read it?
Yeah.
same way
Well,
that-
Aristotle was left-handed. I'm saying, how do you grammatically read not?
Oh, so all he's doing is he's taking two statements, codifying them, and then writing it out. But you're saying, how would you read this? Let's see, what was A? Aristotle was left-handed. It is not the case that Aristotle was not left-handed or Leibniz was left-handed.
Okie dokie.
Not the case. Aristotle was not left-handed.
Such ill relevance.
But no one actually knows what that means, but
See? And you should be able to now determine exactly what that means.
Right. You
But even
can.
it's like
You can intuitively not make sense of that, but you can make sense of it when
Yeah.
you do your tables.
Well, yeah, of course.
That's not always the case.
it's the reason
When you
use
do
the
proofs,
table.
typically, okay, that's intuitively makes sense, now let's go prove it. This is, it does not intuitively make sense. Let's figure out.
Well,
Oh, it's true.
oftentimes, oh, are you saying once you write it out like this, maybe I'll check what you're saying. I thought you were saying when you read it as these full sentences, it doesn't make sense, but when you look at it in this notation, it makes sense.
When he was saying the two
No,
tables.
it's table.
True tables.
Oh, you're saying it's not intuitive to you that this and this are the same thing?
No.
It will be, because you're just distributing the not.
I can see that, but it changes or to and, which is a pretty big deal.
Did we talk about that last class though?
We did.
I don't know,
Still.
but we definitely talked about in discrete math. That's a very common operation.
Right, I know. If I do. But yeah.
If you knew, then yeah, you know it.
That's a tautology.
If Jacob knows this, then Jacob knows this. Yes. You just barely gave us the x implies x tautology.
Nah.
All right. What time is it?
9:30.
Oh geez, it's longer than I thought. Oh, and that's the end. So that was the last one he goes over in the book.
So this is our homework right here.
Yeah, so here's your homework. Just do the exercises at the end of chapter 1. And then we'll just randomly pick each one of you guys to do one of them until we get through the exercises at the beginning of next class and then start the next material.
Okay.
So be ready for rounds.
I'll bite a bullet. Got it.
And you don't know which problem you're doing.
Yeah.
So, do them all.
So you better be ready to do them all. Because if we have to come here and sit here and wait for you to figure out how to solve a problem that was your homework, it's going to be embarrassing for you. I will take the time to personally edit that video and put a donkey face over you with the jackass. Do you want that? I might be tempting people now.
Dude, with
Don't make me do that. I don't want to.
With your fan base, I'd be worried.
You guys? Sometimes on a really bored day. So I think we're done with the lecture. I guess we have some time. We can start these right now.
No,
It's 9:30.
you're good.
You're pretty done? I need to sit down. That's all I care about. But if you guys want to be done, that's fine with me too.
We could, but I mean.
I got